Okay, so look, so it used to be a very informal seminar, but now it's becoming a little bit more formal. And for most of you who haven't met James, I'll just say, well, I'm very happy to have James Walsh giving us a talk today, and James is now a postdoctoral fellow at the Department of Philosophy at Cornell, but I understand he's speaking to us from California. And well, and you see the title. So welcome, James.
Okay. Well, thank you for the invitation to speak here. And thanks to all of you for coming today. I see a few familiar faces and a few unfamiliar faces. The material I'm presenting today is from joint work with Fedor Pakamov. And let's see, the topic of today's talk are the reflection principles. So there are two types of principles that frequently get called reflection principles in mathematical logic, at least two types. And I'm going to be talking about both types today and the relationship they bear to each other. So first we have the syntactic reflection principles. Now, according to a syntactic reflection principle, roughly, if phi is provable in T, then phi is true. So what I have right now is an informally stated principle. It has a truth predicate, so there are real obstacles to formalizing this and a lot of choices to be made. What we often do is we work with formalized variants of this principle or formalized approximations to what this principle seems to be expressing. Why is it called a reflection principle? So I think the idea is that for a suitably chosen theory T, we can recognize the truth of the syntactic reflection principle by reflecting on our practice. So for example, if T is PA, we think, well, why did we choose the axioms? We chose them because I thought they were true. The rules of inference were supposed to be truth preserving. And so this syntactic reflection principle looks true. Okay, so what are the formalized variants that we work with? You may have seen some of these. So the local reflection principle, RFN sub T, is a schema. It consists of every statement of the form, if T proves phi, then phi, where phi is a sentence in the language of T. So in general, T will not be able to prove all of its local reflection principles. For instance, the consistency statement for T is going to be provably equivalent to a local reflection principle. If contradiction is provable, then contradiction holds. So if you take a theory T and you add its local reflection principles, you'll get something stronger, but maybe not much stronger. You can get something a lot stronger by resorting to the uniform reflection principle. So uniform reflection, capital RFN sub T, this is the schema you get where you allow parameters in the formula. So you say for every x1 through xn, if T proves that phi holds of x1 through xn, then phi holds of x1 through xn. So this is the schema you get by adding in every principle of that form, every statement of that form for a formula in the language of T. Now, if you take a theory T and you add this, you will get all the local reflection principles and in fact, much more. So what are the applications of these syntactic reflection principles? So one application is for showing non-finite axiomatizability. So you can show on the basis of Gödel incompleteness type considerations that the uniform reflection schema is not finitely axiomatizable. And what that means is that if you can show that a theory is equivalent to a uniform reflection principle, you've thereby shown its non-finite axiomatizability. So for instance, you can show that PA is equivalent to uniform reflection for some weak arithmetic theories over those weak arithmetic theories. And this provides a syntactic proof of the non-finite axiomatizability of PA. Another application is that people have been interested in reflection principles as a systematic means of extending theories. So the thought here is, people put it in different ways, but the thought here is, suppose I endorse the axioms of a theory T. Well, the theories we're talking about are all incomplete for Gödel type reasons. So how do I extend T? Well, if I endorse T, presumably it's safe to endorse its reflection principles and then to endorse their reflection principles and so on. So people have studied in a lot of detail the hierarchies of theories that get engendered in this way. I'm going to come back and talk about some of these results a little bit later. Okay, so those are two applications. Now, the semantic reflection principles are a little different. So according to the semantic reflection principles, roughly speaking, if phi is true, then T plus phi has a model. Okay, so again, this is an informally stated principle. Usually we work with formalized versions of this principle, approximations to this principle. Why is this called the reflection principle? So here it's actually a different reason. So the thought here is that the set size structures are a reflection of the ambient universe, right? So if phi is true in the ambient universe V, then in fact, this is reflected in some thing inside V. So let me give you an example of a semantic reflection principle. This is from set theory. This is called Montague Reflection. Now, there are many different versions of this principle. There are many things that in the literature get called Montague Reflection. So you might be familiar with some other version, but here's one version. So it's a schema. And it's every sentence of the form. For each M0, there is an M extending M0, such that for any finite choice of parameters and choice of finitely many parameters in M, there's a formula phi that's true of those parameters after relativizing the quantifiers in phi to M, if and only if phi holds of those parameters in V, okay? So what this says is for any set, you can extend it to a set which makes phi true if and only if phi is true, roughly. So you get this sentence for every formula in the language of set theory. Sometimes it's part of this schema. Sometimes you'll see it demanded that the set N be transitive or that it be a rank initial segment of the universe. There are lots of different versions. So what are the applications of these semantic reflection principles? Well, one application, again, is to show non-finite axiomatizability. So for instance, every instance of Montague reflection is provable in ZFC. And you can use this to show the non-finite axiomatizability of ZFC. Right, because if ZFC were finitely axiomatizable, it'd be axiomatizable in a single sentence. It'd just take the conjunction of the axioms. And then ZFC would prove that there was a set that made those axioms true. Right, so it would give its own proof of its own consistency by showing that it had a model. So this is an application showing non-finite axiomatizability. And again, another application has been to study systematic ways of extending theories. So as I mentioned, you can put lots of bells and whistles on these reflection principles. And people have studied reflection principles that you get this way that have large cardinal strength and the hierarchies of principles that you get this way. So for example, Tate argued that in fact, the theories that you can axiomatize roughly with principles of this form exhaust the theories that can be justified on the basis of the iterative conception of set. So people have studied the hierarchy of theories you get this way. Okay, so those are the two kinds of principles. Now I have an interesting quote from the paper of Kreisel and Levy. So they wrote, while local reflection and uniform reflection are called reflection principles, because reflecting on the meaning of the provability predicate for S, we can assert the soundness of S, Montague reflection is called a reflection principle because the set reflects the situation in the whole universe. as far as phi and its subformulas are concerned. The authors cannot agree on whether this is merely a pun. So apparently one of them thought that, these are called reflection principles for different reasons, and you shouldn't read much into it. It's just a terminological coincidence. And one of them saw some significant connection between them. Now, if you're just looking at the formalized variants of these principles, they'll be different. But I think if you're looking at just the informally stated principles, the completeness theorem yields a very straightforward but informal argument that the principles coincide. So here's the argument. So I'll show you how to derive the semantic principle from the syntactic principle. So just assume the syntactic reflection principle for t. So if t proves phi, then phi is true. By contraposing, we get, if not phi is true, then t doesn't prove phi. Whence, if not phi is true, then t plus not phi is consistent. And then we apply the completeness theorem. Right? Consistency gives us a model. So if not phi is true, then t plus not phi has a model by completeness. So if you want to reverse the argument, you appeal to soundness instead. So you can get the semantic out of the syntactic and vice versa. Of course, if these are schemas, then, right, I had syntactic for phi, I get semantic for not phi, but if these are just schemas that apply to every formula, this suffices to give you the principle for every formula in the language. This has the feel of the Kreisel squeezing argument for those of you who have seen this. Okay, so there's some reason to think that there's a real connection. Now, today's goal is I'm going to isolate formalized versions of these principles, formalized versions of syntactic and semantic reflection principles that are of independent interest. I'm going to prove that they're equivalent, at least in a large swath of cases. And the proof does go through a version of the completeness theorem. So to get the semantic reflection principle from the syntactic reflection principle, we'll go through a version of the completeness theorem, but for a proof system that's much richer than first order logic. So that was the introduction. In the next section, I'm going to formulate the reflection principles. There are some real technical difficulties with formulating these principles, so I'll say a little bit about that. Then I'm going to prove the equivalence. And the tough direction is really reducing semantic reflection to syntactic reflection. So I'll explain how we get this reduction principle for semantic, in particular, omega model reflection. And finally, I'll turn to some applications to ordinal analysis. Okay, so that's the plan. So here's a syntactic reflection principle, pi11 reflection for t. So pi11 reflection for t says that for every pi11 sentence phi, if t proves phi, then phi is a pi11 truth. So remember, pi11 is the complexity class that we get from a universal set quantifier and an arithmetic matrix. The pi11 truth predicate and pi11 reflection principle can be formulated in ACA 0. And we're going to be interested in what happens when we iterate the pi11 reflection principle along ordinals. So we're interested in the theories of alpha iterated pi11 reflection over t. That's how I'm going to pronounce that pi11 r to the alpha of t. So what is this? So I'm going to give an informal characterization first. So 0 iterated pi11 reflection over t is just the theory t. And for alpha greater than 0, alpha iterated pi11 reflection over t is t. And then you add in the pi11 reflection principle for all the lower iterates. So you add in the statement that beta iterated reflection is pi11 sound for each beta less than alpha. So the rough idea is, you start with 0 iterated reflection as just the theory t. You add in its pi11 reflection principle. Then you add in that theory's pi11 reflection principle, and then so on, and you take unions at limit stages. That's the idea. Now, to formalize this, you need to be a little bit careful. So notice that on the right-hand side of the second equation, I have pi11 reflection applied to what? Well, applied to beta iterated reflection, it says. But pi11 reflection can not really be appended to a theory, as it were, directly, but only through a presentation of the theory. So to make this precise, we have to fix some presentations of these theories. So for example, if alpha were omega plus 1, and we wanted to know what's the statement that omega iterated reflection is pi11 sound, we would need some way of representing omega, so we know what omega iterated reflection is. So the way that we do this is we appeal to the fixed point lemma. So we can define the formula phi is an axiom of alpha iterated reflection. This is a formula in 3 variables, phi, alpha, and t. We can define this in ACA 0 using the fixed point lemma. The definition, I'm not going to give you the most explicit syntactic definition because it really does just formalize an intuition that's already codified in the in those equations. So it says phi is an axiom of alpha iterated reflection over t if and only if phi is an axiom of t, or for some beta less than alpha, where this less than is given through an explicitly chosen ordinal notation system. Phi is the statement that beta iterated reflection is pi11 sound. Now note that the occurrence of beta iterated reflection in the right side, this is actually, we're putting in the Gödel number of the theory that's defined by the formula is an axiom of beta iterated reflection over t. So this is what the fixed point theorem allows us to do, is we can use the Gödel number of the formula we're defining on the right-hand side. That's what's going on. So what about the semantic principles that we're interested in? So remember that an omega model is an L2 structure. That is a structure for the language of second order arithmetic with a standard first order part. So the first order quantifiers are ranging over n, and the first order functions are standardly interpreted. The second order part of an omega model is going to be some subset of the power set of n. And we're going to be interested in the principle that says every set is contained in an omega model of t. Every set is contained in an omega model of t. So this is a principle that shows up a lot in reverse math. So for example, the following equivalences are stated over RCA 0. ACA 0 is equivalent to the sentence that every set is contained in an omega model of RCA 0. Equivalently, ACA 0 is equivalent to the claim that every set is contained in an omega model of WKL 0. ATR 0 is equivalent to the claim that every set is contained in an omega model of sigma 1, 1 choice. The theory ACA 0 plus, which says that every set is contained in an omega model of ACA 0. This is also widely studied. It shows up in the reverse mathematics of Hinman's theorem. I guess it's currently the weakest known system that proves Hinman's theorem, I believe. Okay, so this principle that every set is contained in an omega model of T is a principle that shows up in across reverse mathematics. Lots of theories can be axiomatized in this form. So our result is roughly the following. It says that for pi12 axiomatizable theories T, the following are equivalent. First, that every set is contained in an omega model of T. And second, that for every X, if X is a well ordering, then X iterated pi11 reflection for T is pi11 sound. So this second claim says you can iterate pi11 reflection for T along any well ordering. and it doesn't go wrong, you still get something pi11 sound. You get arbitrarily iterated pi11 reflection. So if you were to look at the first principle, you see that this is a pi12 statement, right? For every set, there exists an omega model. And as we saw, I mean, this is a comprehension principle. It has set existence consequences. You can axiomatize lots of theories in this form. Now, if you were to look at a specific iteration of pi11 reflection along a presentation of an ordinal, you would get a pi11 theory. It would not have set existence consequences. But the way we stated things, arbitrarily iterated pi11 reflection, you do get set existence consequences out of this. It is a comprehension principle. Why? Well, it says for every x, either you get this amount of reflection or x is not well ordered. So we can get lots of descending sequences out of this principle. That not well ordered is sigma 1, 1. Okay, but the principle as stated is actually not quite clear. So what does it mean to iterate reflection along an arbitrary, potentially non-recursive, well-ordering x? So before, what we did was we fixed a presentation of an ordinal, an effective presentation of an ordinal, and then we defined the iterates up to that length. But now we're making claims about arbitrary iterations of reflection, and we have to say what that means. Now, if you look at what's going on here in sentence number 2, you see that the variable x, which is being quantified out, is occurring within the scope of pi11 reflection. So we have pi11 reflection being applied to something that has this variable x in it. And that's really the source of the problem here. So I'll explain how to get around this problem. So in the study of reflection principles and provability in first order arithmetic, we can consider provability applied to formulas that have number parameters. Like for every x, PA proves phi of x. So we saw this before in the uniform reflection principle. We had something like this written. What does this mean for every x, PA proves phi of x? Well, the reason that this makes sense is because every single number has a name in the language of PA, a canonical name. 0 is named by 0, and 1 is named by s of 0, and 2 is named by s of s of 0, and so on. So what this is saying for every x, PA proves phi of x, is we can prove phi of with 0 plugged in, and phi with s of 0 plugged in, and phi with s of 0 plugged in, and so on. So this dot bracket phi of x denotes the Gödel number of the formula phi of x bar, where x bar is the numeral you get, s of s of s of s, x many times, applied to 0. But in the context of second order arithmetic, this doesn't make really any sense. For all x, ACA 0 proves phi of x. We don't have numerals for the sets. We don't have a canonical name for each set. So what does it mean? We need some other approach to pass the second order variables in the scope of the provability predicates, inside the provability predicates. That's the problem. And the approach is to simply enrich the language. So what we're going to do is we're going to use this language boldface L2. And this extends the language of second order arithmetic with a set constant, C sub A, for each set A. So we just add in a name for each set, a canonical name. Now, from the external perspective, of course, this is a continuum-sized language. We've added a set for each, a constant for each set, for each real. But the key here is that the boldface L2 formulas, they can be encoded as sets and reasoned about in ACA 0. So lightface L2 formulas, through Gödel numbering, right, they can be encoded as numbers. But the boldface L2 formulas, they can be encoded as sets. Now, how does that work? So suppose I have a boldface L2 formula, phi of C sub A1 through C sub AN. So if I want to encode that into a set, I have to keep track of phi, I have to keep track of the light face formula, phi of X1 through Xn, right? So that's just a number to keep track of that. And I have to keep track of the sets that are named, A1 through AN. And the thought is this: you can encode finitely many sets into a set. Just, the usual, encode them in the slices. And then you'd have to keep track of the numbers. So just put that first or something, keep track of that as well. So you can encode this boldface formula as a set. Theories are now countable sets of boldface L2 formulas. And I should mention that the standard syntactic operations on formulas, forming conjunctions, forming disjunctions, performing substitutions, these correspond to arithmetic operations on the codes of the sets, which just means that all the standard syntactic observations you'd like to be able to make in your theory about formulas, these can be made in ACA 0 about the boldface L2 formulas. So you can reason about them in a very natural way in ACA 0. Now we can in ACA 0 give definitions of the standard complexity classes and their reflection principles for this boldface language. So boldface pi11 reflection of T, this is the sentence that says all boldface pi11 theorems of T are true. So that is, for every phi in boldface pi11, if T proves phi, then phi is a boldface pi11 truth. And I won't give the technical fixed point definition, but using the fixed point lemma, we give a definition of theories of alpha iterated pi11 reflection over T. So informally, alpha iterated pi11 reflection over T is T, and then you add in the statement that beta iterated reflection is pi11 sound for all the beta less than alpha. And now we can state the theorem. Provably in ACA 0, for any boldface pi12 axiomatized theory T, the following are equivalent. First, that every set is contained in an omega model of T. And second, that for every X, if X is a well ordering, then X iterated pi11 reflection is pi11 sound. Okay, so that's the theorem.
Quick question, James.
Yes.
So you need ACA 0 to do the arithmetization of the language. Is that what ACA 0 is for?
Yeah.
And RCA 0?
Yeah. So I mean, even with the lightface language, dealing with the complexity class pi11 requires ACA 0.
Yeah, just to have a true definition for pi11, you need to have
Yes.
ACA 0, because otherwise there's an issue with the first order quantifiers.
Exactly. You can't scolemize them that way. You don't get those normal form theorems.
Oh, all right, thanks.
Yeah.
Can I ask a question also?
Sure.
About the formalization of the notion of omega model.
Yeah.
In second order arithmetic. So
okay.
Any model of second order arithmetic thinks that it is an omega model, is that right? No, but you need to formalize what an omega model is to state this. Yeah.
So all the omega models we're talking about are countable coded omega models. So it's a set that's just encoding countably many sets.
Oh, you code the model as a single set. Okay.
Yeah, exactly.
Okay, thank you.
Yeah. Okay. So we have so we have this equivalence. The restriction to pi12 axiomatized theories is necessary. Here, and the proof of 2 from 1, so 1 implies 2, is relatively straightforward. but the 2-to-1 direction depends on two completeness theorems for an infinitary proof system P. So I have completeness wrapped in quotes because their completeness results in different senses of the word completeness. Okay, so let me explain how those how this proof goes. So we developed this proof system P. What is a proof in P? So the proofs are well-founded trees. So it's very common to think of a proof as a tree. So the nodes in the tree are decorated with formulas. The root of the tree is decorated with the thing that's being proved, and the leaves of the tree are decorated with the axioms. And if you have two nodes in the tree that have a successor, and you look at the way they're decorated, it has to make sense in virtue of some inference rule of the proof system. So for instance, you might have something like phi, psi, and then you get phi and psi. So we'll have a rule in our system that allows this to happen. The proofs are well-founded, so you don't get any infinite paths through the tree. If you start stepping back, it always terminates in some axioms. Our proof system is infinitary, and in particular, we have a version of the omega rule in our system. So the omega rule says from phi 0, phi 1, phi 2, and so on, all the way up, you get to infer for every x phi x. So this means that there are, in particular, we have this rule that has infinitely many premises. So there will be times when a node has infinitely many predecessors in the proof. This rule is, we're trying to develop a proof system that's sound and complete with respect to omega models. So this rule is sensible. Now, one thing I should say is that nodes are not really decorated with formulas exactly. They're decorated with sets of formulas called sequence. So if you prove a set of formulas in this system, think of it as meaning something like one of the formulas in the set is true. So it has this sort of disjunctive interpretation. And we set up the proof rules in such a way that they make sense with respect to this interpretation. Now, I'm going to be mentioning, sorry, just look at the last condition here before the statement of the theorem. I'm going to be mentioning things about cut-free proofs. So roughly, and I'll say some things a little more precisely, the cut-free proofs don't have applications of modus ponens, right? So modus ponens, phi implies psi, phi, therefore psi. A cut-free proof will not have modus ponens in it. Now, there are, in fact, many generalizations of modus ponens that get called cut rules. And for those of you who know what they are, we won't have any of them in our system. But the point is this: if you look at modus ponens, there's this formula phi that occurs in the premises and doesn't occur in the conclusion. It gets cut out of the proof, and we don't want that. So we are we're going to be careful to state when we're talking about cut-free proofs in certain circumstances rather than proofs with cut. Now, this technical point does matter to the way that these results are stated, but for those of you who just want to think in terms of proofs, you can probably ignore this technical complication. If you're not sensitive to it, it won't matter much for understanding the statements at their core. So the first theorem is a completeness theorem, sort of in the sense of Gödel's completeness theorem. And it says the following: for any set gamma of sentences, so for any sequent gamma, the following are equivalent. First, that gamma has a cut-free proof in P. And second, that there exists a family S of sets such that for any omega model containing S, M satisfies one of the sentences in gamma. This is a bit of abusive notation. That's what that means. So this is a completeness theorem in the sense of Gödel completeness for with respect to cut-free proofs for this, this system of omega logic. Okay, so that's the first theorem. Now the second result is a completeness result in the sense of Pefferman's completeness theorem. So Pefferman proved that for any true sentence phi of first order arithmetic, there's a presentation alpha of a recursive ordinal such that you can prove phi by iterating uniform reflection schema up to alpha, starting with PA. So this is called the completeness theorem because it shows that iterated reflection is complete in a certain sense. And I mentioned before that people have been interested in studying the hierarchies of theories that you get by iterating reflection principles. And this is one of the central results in that area. So we want to prove something like this. We want to show that iterated reflection principles are complete in some sense. So before stating the result, let me just mention that there is a uniform way of associating linear orders to trees. And in ACA 0, you can prove that whenever the tree is well-founded, it gets the linear order that it gets associated with is an ordinal, is a well ordering. These are called the Kleene-Brouwer ranks. So the Kleene-Brouwer rank of a well-founded tree will be the ordinal that it gets associated with in this way. So now we can state the theorem or the lemma. So lemma is this. Suppose T is boldface pi12 axiomatized theory, and gamma is a set of boldface pi11 formulas, and that there is a cut-free proof of gamma from T in P with Kleene-Brouwer rank delta, then delta iterated boldface pi11 reflection over T proves gamma. So let me just explain in a little more intuitive level what this lemma is saying. So the lemma says this: pick T and gamma of appropriate complexity. Okay, so now we're going to suppose that we have a proof in our system, right? So we have a proof in our system. It's a well-founded tree. The axioms are from T, and the conclusion is gamma. So we were able to prove gamma from T by using this proof system, which has the omega rule in it, right? Okay, this is a well-founded proof. So it has some Kleene-Brouwer rank, delta. Then the claim is you can also prove gamma, just in first order logic, by iterating pi11 reflection, starting with T up to delta. That's the claim. So what's going on is, in the proof of this lemma, we show that roughly the applications of the omega rule can be replaced with iterations of pi11 reflection. So that's the idea. Okay, so now.
Wait, sorry, can I ask a question?
Sure.
Can you just say something about, I mean, what's the complexity pi12 and pi11? Why those complexities specifically?
Right. So relevance to the theorem as a whole, or to this lemma, you mean?
I guess, I mean, like, what are you using about the, I mean, could you just do it with, you know, pi16 and pi15 or something like that? Or what's being used about pi12 and pi11 here?
Good, yeah. So, okay, so so let me just, I'll say first, we do have generalizations of this result to other complexity classes. But you need to be a bit careful about exactly the way you state things. Right, but there is a technicality here. If T had higher complexity, you wouldn't be able to know just from iterating pi11 reflection what was going wrong. So if T had higher complexity, you would have to iterate, say, pi12 reflection or something like that, or pi13 reflection.
James, I don't think it's true. I think it's really we do have this kind of result only for pi11. I mean, so the point is that so basically so methodologic. So it's completely with respect to complexity class pi11, but not with respect to high complexity classes. So basically this should be a limitation.
Sorry, so I think I maybe I misstated what I meant to say. But I mean, we do have generalizations of this result for the higher complexity classes.
Oh, okay.
You know the ones I'm talking about. But
actually, I'm not precisely sure. But okay.
Yeah. So I mean, I can. I don't want to get the statements exactly wrong right now, so I can say something about this later. But what were you saying about where the proof goes wrong when we don't have the pi12 restriction here?
Okay, so so basically, so exactly, so you could prove this simply by simply using the fact that so omega proofs are pi11 complete. So then for particular pi11 sentence, you will have a particular well-founded proof of this fact. And then when we iterate so reflection along the linear power order for this proof, so we get our result. But the point is so that sorry, it's really my bad. So I misunderstood what the lemma is. So yeah, it's all should be right. Yes, I'm really sorry.
Yeah.
Yeah, so I saw that. So it's about true pi11 sentences, but no.
Yeah.
It's fine.
Yeah, I mean, in a way, it's part of why I was hesitating is because this way we state this is a little different than, say, the way we state it in the paper, because I wanted to avoid some technicalities about what's going on. But maybe I can come back to this later.
Okay, thanks.
Okay. Yeah, so now the question is, how do we derive omega model reflection from iterated pi11 reflection? And so the thought here is we're going to assume that we can iterate pi11 reflection arbitrarily. So that means for every x, if x is a well order, then x iterated pi11 reflection is pi11 sound. And we're going to let x be a set. So we want to find an omega model of T that contains x. And the thought is that we're going to break up into cases. So in the first case, case one, there's no cut-free proof in our system of a contradiction from T. And then by the completeness theorem, so consistency gives us a model, we get that there is an omega model of T containing X. So if there's no cut-free proof of a contradiction from T, then we get what we want. So the second case, there is a cut-free proof in our system of a contradiction from T. But then by the lemma, we can prove this contradiction by iterating pi11 reflection up to the CUNY-Brouwer rank of that proof. But then that contradicts our assumption. Our assumption was that we could iterate pi11 reflection arbitrarily far. So case 2 doesn't happen. We're just in case 1. So from arbitrarily iterated reflection, we get an omega model containing the set. So that's the idea of the proof. So let me just state the theorem again. So the theorem gives us this equivalence between omega model reflection and arbitrarily iterated pi11 reflection. Now I mentioned that the first principle is a comprehension principle, and we see it a lot in reverse math. But the second principle opens the way to connections with ordinal analysis, because there's a very thorough understanding of theories of iterated pi11 reflection in terms of their proof-theoretic ordinals. That is, we know how the proof-theoretic ordinal of theory will grow as a function of the amount of pi11 reflections you started adding. So this opens the door to ordinal analysis and ordinal analysis related results of theories of the form 1. So what is ordinal analysis? So this T sub WO, this is called the proof-theoretic ordinal of T. And the classic definition is that the proof-theoretic ordinal of T is the supremum of the order types of the T provably well-founded primitive recursive linear orders. So it is a mouthful, but just a few words. So T sub WO it's an ordinal. It gets associated to a theory as, we think of it as a measurement of the strength of the theory. This is one way of thinking about it. It tells you what kinds of pi11 statements the theory proves, because it tells you which ordinals, roughly, are well-founded, provably well-founded in the theory. So the proof-theoretic ordinal measures something about the pi11 theorems of the theory, but we want to get something that measures the pi12 strength of the theory. So we introduce the notion of the dilator of a theory. So the dilator of a theory, T, is a function that, roughly speaking, encapsulates the closure conditions that T imposes on the ordinals. So the definition here, the proof-theoretic dilator of a theory T is a function which maps the order type of alpha to the proof-theoretic ordinal of T plus the statement that alpha is well-ordered. And alpha here is ranging over countable linear orders. So we write T sub boldface pi12 to denote the proof-theoretic dilator of T. So, let me say just a word about this. So,
James, just a very simple thing. Sorry. Why order type, not just alpha?
Because just to make sense of what's written on the right-hand side.
Oh, I see, because you need to have some representation of it. Okay.
Yeah. So let me just say a word about this to give an intuition. So roughly, the proof-theoretic dilators is taking alpha, right? And it's telling us what is the proof-theoretic ordinal of T plus the statement that alpha is well-ordered. Now, suppose that T imposes this closure condition on the ordinals. Suppose that T proves, or it imposes that the ordinals are closed under the function G, right? Well, if T is imposing that the ordinals be closed under the function G, then the proof theoretic ordinal of T plus the statement that alpha is well ordered will be at least the next ordinal above alpha that's closed under G, right? So that's why the dilator is encapsulating something about the closure conditions that the theory is imposing on the ordinals. We want to know if I add the statement that this is well ordered, how much more am I going to get bumped up? Okay, so that's the idea. So just to give an idea of where this is going, we have a systematic connection between Pi-1-1 reflection and proof theoretic ordinals. So we can get a connection between closing off under Pi-1-1 reflection and closure conditions on the ordinals. And the main theorem thus establishes a connection between omega model reflection and closure conditions on the ordinals. That's the hope. That's the hope. And we want to use this connection for some applications. So we can measure the connection between the proof theoretic dilators and the omega model reflection using the Veblen functions. So the Veblen functions are often used to measure the strength of theories in proof theory. Before giving the definition, let me mention a fixed point of a function f on the ordinals is any ordinal alpha such that f of alpha is alpha. And here's the hierarchy. So we have a hierarchy of functions on the ordinals, and the functions are going to be indexed by ordinals themselves. So phi sub 0 of gamma is going to be omega to the gamma. That's the first function. Phi sub alpha plus 1 will enumerate the fixed points of phi sub alpha. So for instance, phi sub 1 of 0 is going to be the least fixed point of phi sub 0, and that's epsilon sub 0. Then phi sub 1 of 1 is going to be the next fixed point after that, which is epsilon sub 1. So phi sub 1 is just the epsilon function. It's just enumerating the epsilon numbers. Phi sub 2 will then enumerate the fixed points of phi sub 1. So phi sub 2 of 0 is going to be this number epsilon sub epsilon sub epsilon sub epsilon sub epsilon, all the way down, right? And then at the limit stages, you enumerate simultaneous fixed points of all previous functions. So phi sub lambda will enumerate the ordinals that are fixed points of phi sub delta for every delta less than lambda. So these functions, as I said, they're used a lot in proof theory to measure the strength of theories, but that's actually not even where they arose. So these functions were isolated before even the ZFC axioms. Now phi sub alpha plus of beta is going to be the least ordinal that's greater than beta and in the range of phi sub alpha. So phi sub 1 plus of beta will be, for instance, the least epsilon number that's greater than beta. Now, when I state these theorems, I'm going to appeal to these theories. I'm not going to go into the detailed fixed point definitions, but omega RFN of T says every set is contained in omega model of T. Omega R to the alpha of T is this result of iterating omega reflection along alpha starting with T. And these are the theorems. So first, we have that the proof theoretic dilator of ACA 0 is phi 1 plus. What that means is that the proof theoretic ordinal of ACA 0 plus alpha is well-founded will be the least epsilon number above alpha. So that's actually it's not so surprising, but I just put it here so that we can make sense of some things that I say in a moment. So here's the theorem. For any linear order alpha, alpha iterated omega reflection over ACA 0 has proof theoretic dilator phi sub 1 plus alpha plus. So we have this statement of how proof theoretic dilator grows as a function of iterated omega model reflection. Now, so with the indexing, why is it 1 plus alpha? And, you know, it's just, this is why I have the other theorem. You know, we already start with 1. When we start with ACA 0, the base case already has 1 there. Okay, so this connection yields uniform proofs of a bunch of results from ordinal analysis and some from reverse math in this interval of theories from ACA 0 to ATR. So I have here some results from ordinal analysis. ACA 0 plus has proof theoretic ordinal. So we get new proofs of these results. So proof theoretic ordinal of ACA 0 plus is phi sub 2 of 0. Proof theoretic ordinal of sigma 1 1 choice with full induction is phi sub epsilon 0 of 0. Proof theoretic ordinal of ATR 0 is gamma sub 0. Proof theoretic ordinal of ATR, so arithmetical transfinite recursion with full induction, is gamma sub epsilon 0. And so gamma sub alpha is this sort of fixed point that's defined in terms of the whole, in terms of the Veblen hierarchy, definition of the Veblen hierarchy. So gamma sub alpha is the alphath ordinal number beta, such that phi sub beta of 0 is beta. So for instance, gamma sub 0 is, it's the supremum of this sequence, phi sub 0 of 0, phi sub 0 of 0, and so on. So they're very big, they get very big. And we also get some results from reverse math, now over the base theory ACA 0, but I'll mention what these results are. They're results to the effect that a certain operation preserves well-orderedness. So we get an alternative proof of this theorem from Marconi and Montalban, that ACA 0 plus is equivalent to the statement that for every alpha, if alpha is well-ordered, then so is phi sub 1 of alpha. And we also get a result from Harvey, Friedman, Montalban, and Weiermann, which is that ATR 0 is equivalent to the statement that for every alpha, if alpha is well-ordered, then so is phi sub alpha of 0. So now the alpha going into the subscript. And those are the applications I wanted to talk about. So thank you very much for your attention.
Okay, thank you very much. And time for questions.
Hello?
Hi.
I have a slew of questions, actually, but let me ask the last one first. Then I'll give the floor to the others, of course. One of the exciting things here is that you're making very tight and crisp the association of ordinals with theories. You know, a thing that has often been much murkier in the past. For example, Girard, whose name comes to my mind a lot, isn't he the author of Dilators?
Yes, he has a notion
anyway,
of dilator. Yeah, that's right.
Yeah, yeah. But he had a result once showing that gamma 0 could be the ordinal of Peano arithmetic if you looked at a hierarchy of, you know, of recursive function hierarchy that went very, very, very slowly. Is that connected at all with your results on gamma 0 here?
I don't know anything about that result. Maybe Fedja, do you know about this?
Yes, I don't know. In Girard result, it wasn't gamma 0, it was Bachman-Govert ordinal. So Bachman-Govert ordinal in fact is much larger than gamma 0. So but in certain sense, okay, of course there's some connections. Yeah. But talking about how what we are doing is connected to this particular result of Girard. So Girard result was basically heavily based on dilators. So in a sense, of course, we also doing something that's we also using dilators, but I don't see some closer connections in this.
I do think, I mean, one of the things that you said in the beginning is true, that we've been trying to get, I mean, and actually this project came out of a previous project that the two of us had worked on. And in both cases, we are trying to get, yes, very systematic statements about proof theoretic ordinals of theories that are kind of, you know, relatively independent of presentation and those kinds of clerical matters.
Yeah. That used to drive Girard crazy, though, that sort of thing. I have another question about names. At the very beginning, your local reflection makes one think of Lerp's theorem and makes one think of Ulf-Schmerl's theorem, a sort of extension of Lerp's theorem. Can you say something about the connection and that work and your work?
So I mean, I see the connection with Lerp's theorem. So Lerp's theorem says that an instance of local reflection is only provable in a theory if the consequent, or if the consequent of the local reflection principle is provable. I don't know the result of Schmerl you have in mind. Maybe Fedor does.
It was something like provable phi implies phi, parens, implies phi. If it's provability implies,
you might, I see. I think I know what you're talking about.
Ah, good.
So there is a technique that Schmerl came up with, which is called reflexive induction. And reflexive induction is a way of using Lerp's theorem to simulate proofs by transfinite induction in these kinds of systems. And it does, I mean, when you look at the proof, it does sound like what you just said, and it looks like just sort of black magic using Lerp's theorem. We use this proof technique in just about to prove every single result in the paper. I mean, maybe not every result, but effectively every result. And the same was true of our previous paper on this topic. So yes, we do use that all the time.
Okay. Any other questions? Okay, so if there are no questions, well, let's thank James very much for the talk. It was an excellent, very clear and interesting talk. So thank you very much. And I just want to say that from now on, I think we have a full schedule, almost full schedule, almost until middle of April. So pay attention to announcements from Vika. And we have our program on the MOPA page with the abstracts and titles. And if you miss a talk, the talk will be recorded. So I'd like to see all of you there. And if anyone who hasn't given a talk yet, or maybe anyone who has already given a talk feels like giving another one, let me know. Okay, so thank you again.
Thank you. Thanks for having me.